It is not unusual to see this kind of problem turn up in exams. Using the rules you have just learned, we will assign oxidation numbers to the desired atom in the compound. Perchloric acid contains hydrogen and oxygen atoms, so based on rules 3 and 4, we can assign oxidation numbers to those atoms. Hydrogen in a molecular compound is +1. The oxidation number for oxygen is -2. But there are 4 of them, so the oxidation number applied to O4 is -8. Rule 6 identifies the oxidation number of the chlorine atom. Since perchloric acid is a neutral molecule, the net charge is 0, and so the sum of the oxidation numbers of all the atoms in the molecule must also be 0. If we assign the letter X to chlorine as its oxidation number, then X plus 1 from the hydrogen and -8 from the 4 oxygens will equal 0. Isolating X, we see that it has a value of +7. The oxidation number for chlorine in perchloric acid is +7. Silicon tetrabromide does not contain any hydrogens or oxygens, so we look to Rule 5, in that the more electronegative element is assigned the oxidation number that is the same as their ionic charge. Bromine is far more electronegative at 3.0 to silicon's 1.9. Bromine's ionic charge of -1 becomes its oxidation number in this compound. But there are 4 of them, so the oxidation number of the 4 bromines is -4. Again, assigning X to represent silicon's oxidation number, the sum of X and -4 equals the net charge of the silicon tetrabromide molecule, which is 0. So X equals +4. The dichromate ion has a net charge of -2. We start out the same way, providing an oxidation number for the 7 oxygens. Each oxygen is -2. There are 7, so the 7 oxygens have an oxidation number of -14. The 2 chromium ions would share an oxidation number of +14 if we were dealing with a neutrally charged compound. But since it's a polyatomic ion with a net charge of -2, then when we add the oxidation number of the chromium atoms to the oxygen atoms, we should get -2. After some tinkering with a simple equation, we find the oxidation number for each chromium atom is +6. Well, this is all very nice, but what's the point of oxidation numbers? Hopefully you are seeing that these numbers relate to the relative charge on the atom. A negative oxidation number means that it has more electrons. A positive oxidation number means it has less. If we apply oxidation numbers to each of the atoms in a redox reaction, we can see how atoms on the reactant side gain or lose electrons by comparing their oxidation numbers to the product side. Using the net ionic equation of zinc metal reacting with a solution of copper-2 ions as an example, we assign oxidation numbers to each atom in the equation. The elements have oxidation numbers of 0, and the monatomic ions have oxidation numbers that reflect their charge. Starting with zinc, it goes from an oxidation number of 0 to +2. It has lost 2 electrons, and so zinc has oxidized. Copper ion has changed from an oxidation number of +2 to 0. It has gained 2 electrons, and so the copper ion has been reduced. When asked to identify the oxidizing agent and reducing agent, recall that the reactant being reduced is the oxidizing agent, and that the reactant being oxidized is the reducing agent. Redox reactions involve the movement of electrons in a reaction. This movement of electrons can be tracked by assigning oxidation numbers to the atoms in the reaction. Going from reactants to products, if an atom becomes less negative, which also means more positive, electrons are being lost. And so oxidation is occurring. Another atom will become less positive, which also means more negative, indicating that electrons are being gained, and so reduction is occurring. At first, it may not be immediately obvious that when hypothetical element X starts as -2 ion and becomes a +4 ion, that it's losing electrons. But hopefully, this simple chart from your text and lots of practice will help speed up the process. This problem involves the combustion of methane. There are always redox reactions where the hydrocarbon is oxidized to form carbon dioxide and water vapor. But in case you forgot that combustion reactions are redox reactions, how can you tell reduction and oxidation has occurred in this reaction? First of all, we assign oxidation numbers to all the atoms in the equation according to the rules we learned earlier. Next, we compare the atoms and their oxidation numbers on the reactant side to those on the product side. Notice carbon. On the reactant side, it has an oxidation number of -4. On the product side, carbon is a +4. Carbon has lost electrons and so has been oxidized. The substance undergoing oxidation is the reducing agent. Hydrogen has an oxidation number of +1 on both sides of the equation and so is not involved in electron transfer. Oxygen, on the other hand, is in the elemental form on the reactant side and so has an oxidation number of 0. On the product side, either as part of a carbon dioxide molecule or the water molecule, oxygen has an oxidation number of -2. Oxygen has then gained electrons and so is reduced. The substance being reduced is the oxidizing agent. While the carbon in methane loses 8 electrons, the oxygen gains only 2. Because the combustion reaction equation shown here is balanced, we can see that there are 4 oxygen atoms on the product side. If each gains 2 electrons, then that's 8 electrons gained in all, the same number lost from carbon. Balancing electrons in a redox reaction as a way of balancing a chemical equation is covered in your text, but will not be a part of your assessment in this course.